Thanks for tuning in. I'm Doenges, and I'm going to tell you about Petr4, formal foundations for P4 data planes. Data planes arise in everyday life. When this flamingo wants to communicate with shrimp.net to order dinner, its laptop creates a message. This message makes its way into the internet, who knows how, and it bounces around in there doing who knows what until it arrives at its destination. Let's demystify this. We know that these machines, this laptop and this server, both have network interfaces, which communicate with some kind of local switch on behalf of their respective CPUs. And these local switches are in turn connected to other switches, routers, and what have yous that are connected in the network known as the internet. And all these things do is forward packets. There's more to networking than just forwarding packets. You have to decide where they're going to be forwarded to, and all that. But the responsibility of handling packets is what makes this the data plane. It's the foundation of all networking, but it lacks a semantic foundation of its own. This is largely for historical reasons. Internet protocols, the paradigmatic examples of data planes, were developed by the IETF through a standardization process, not a formalization process. They needed to reach agreement between a large group of stakeholders about what protocols were going to look like and how the internet was going to work. They had to use a process of rough consensus and running code to get agreement without wasting time formalizing things that people might object to in the end. And this worked really well, and internet protocols are quite stable. They're about as stable as anything can get. But modern data planes are a little different because networking has flown the nest. Private networks, owned and operated by a single entity, are able to deploy new data plane networks on a software timescale. They're using these for all kinds of applications: network virtualization, congestion control, in-band telemetry, and even in-network computing. And they're doing this by writing new data plane programs in all kinds of languages. And while many of these languages have been formally studied, there isn't really a common semantic foundation with which to understand data plane programming in general. We think P4 is a great candidate. P4 is a programming language for programmable switches and other data planes, and it can be compiled to many targets due to its flexibility with regards to backend. And in this work, we give semantic foundations to data planes by giving semantic foundations to P4. So what I'm going to do is show you the P4 language with an example and show you some of the subtleties of data plane programming. And then I'm going to move on to our semantic archaeology approach. I'm going to tell you how we went out and studied this language that already existed and extracted some kind of formal artifact from it. And I'll show you our core calculus, and then I'll get on to the implementation, and there will even be a little demo at the end. So for the example, I want to introduce source routing with an ACL. ACL stands for Access Control List, and it's a firewall on each switch that can decide to drop a packet based on the contents of its headers. Source routing works like this. At the source, you specify a route. It's a sequence of ports, and as the packet is forwarded, so at the first switch here, the first port is 2, so it's going to be forwarded out port 2, then port 3, then port 3. This means the source needs to know something about the topology of the network. We're going to program a packet processing pipeline to implement this functionality. It begins with bits, which are parsed into an internal typed representation. Then we define kind of the business logic, which makes a forwarding decision and modifies headers as needed. Finally, we're going to deparse the packet, turning this typed representation back into a string of bits. Before we define these 3 steps in P4, we need to define our types. Our headers are going to look like a type tag, followed by up to 10 hops, and finally a standard header, which is just a source and destination. Parsing these things is done in a state machine format. The state machine begins by looking at the type tag, so it extracts a type tag and then compares it to see what it says. If it's 1, there are hops, otherwise it's just a standard header. For hops, we have 2 fields. There's the port, which is the source routing information, and there's a bottom of stack marker BOS. The BOS is the second byte, and it's 0 in these first two entries and 1 in the last one. It works like a C null terminator in that it being 1 indicates that the parser should stop. So you can see that the parser continues parsing. It parses the first one, it's 0, it keeps going. Parses the second one, it's 0, it keeps going. And finally, it parses the last one, where the bottom of stack marker is 1. Then it continues on to parse the standard header, it's just 2 bytes, and it transitions to the accept state to indicate that it's done parsing. The rest of the packet is the payload, and it's saved on the side for later. For the business logic, we have an ACL table and then a little bit of code to implement source routing. The ACL table can look at the source and destination in the standard header, and it will deny the packet if the source is CC and the destination is DD. And otherwise, it won't do anything. It'll just allow the packet to continue on. The source routing code here starts by assigning the egress spec, which is a way of controlling forwarding behavior, based on the first hop's port. So in this case, it's going to forward it out port 2, because the first hop's port is 2. Then it pops that off the list of hops so that it's no longer there, and then it applies the ACL table. Since this packet is going from AA to BB in the standard header, the ACL won't do anything. Finally, we can deparse the packet, emitting all the headers we've modified back into a binary format. And after the deparser terminates in P4, the payload from before is concatenated onto the packet. So the payload is left untouched. Is this program correct? Well, not really. There's a bug involving the parser, but it's really more of a semantic issue than it may first appear. Consider this packet. There's one hop, and its bottom of stack marker is 0, which means the parser will just keep going. And the internal type representation we get will look nothing like the packet we've written down. In particular, the parser is going to parse 10 entries for hops, and then it's going to run out of space. And when it runs out of space, it'll go to a special reject state, which, depending on the architecture, might still execute the business logic instead of just throwing the packet on the floor. And if it does that, inside of that code, the standard header is going to be uninitialized. And this means that it can return any value. In P4, uninitialized values are basically non-deterministic, and anytime you read from them, you can get something different, which means that this could traverse the ACL despite its real standard source and destination headers. And this is a subtle issue having to do with architecture-specific behavior following parser failures, and with architecture-specific behavior in resolving undefined or uninitialized values. So you need a full semantics of the language that's sensitive to architectures in order to understand this kind of bug. But there are other benefits of foundations too. Of course, program verification is one. So you can do foundational verification of your programs. You can do architecture independent verification. But also you can do compiler verification and preserve those program verification guarantees all the way down to hardware if you like. And there are informal benefits as well. Language design is difficult, and formal insights can help guide development of new features and resolve conflicts in the existing specification that have eluded informal approaches. To that end, we introduced Petr4, which is a reference implementation and a core calculus. The reference implementation is about 10,000 lines of OCaml, and the core calculus is a few pages of pen and paper kind of formalization. The reference implementation is parameterized over architectures, and it's been validated against an existing test suite. The core calculus, on the other hand, is equipped with some meta theory. There's a termination theorem and a language extension case study to show that it's useful for language design. And in developing these artifacts, we didn't have to come up with a lot of kind of new mathematics. P4 is just not that crazy of a language. But we did need to do semantic archaeology. Over the years, programming languages research has produced a kind of PL toolbox of things like operational semantics, type systems, abstract syntax, and all the rest. And this stuff is really useful for understanding real-world languages. It also comes with a kind of PL taste, which is developed. And this can be really helpful in avoiding the pitfalls of PL design, but it can also hold us back. Excavating a language that was developed according to different values and different tastes by different people can challenge your palate, as it were, and each new discovery you come across can seem to conflict with the last, and it can be very discouraging to keep digging in such a situation when each thing you dig up just makes your existing system more complicated. But that's exactly the task of semantic archaeology. You have to keep digging, you have to keep your hands on the toolbox, and produce a consistent, tasteful semantics for this real-world thing that can help people understand it and study it further. For P4, this meant reading a specification and studying an open source compiler. The specification is about 160 pages of English text mixed with pseudocode, and the open source compiler is about 40,000 lines of C++, and that's before you count the header files. So it's a big dig, although not as big as it could be. This isn't C, it's a relatively young language, and it's not too complicated. We tried to understand it through example. So we pick up an example like this, and this is just part of the program so far, and try to understand why it was a correct P4 program, or why it was a type-safe P4 program. So in order to uncover the type system, we started here. We have a function that's a generic, and it takes 2 arguments and assigns the one to the other. Then there's a constant w and a main function. And in the main function, there's 2 variables. The first is an unsigned integer of width w, so w bits. And then there's a 16-bit integer food. And then we call f with x and mm. Now, the first thing I see, using my PL taste, is that this is missing a type argument, this call to f, because f is generic. So there must be some kind of type inference happening here. And we should try to figure out what this type argument is and get a feel for how to deduce this automatically. Looking at the types of x and mm, we see that they're syntactically not the same, but semantically I would think they would be equal, because w is a constant and it's equal to 16, so the width of x should be 16. But when are these 2 types equal? Are they considered equal syntactically, or is this kind of compile time evaluation going to happen? Of course, once we do that, we see that we can give these both the type bit 16, and the type argument here can be bit 16. There's another issue here which is less obvious in the surface syntax, but these constants are all unsigned infinite precision integers. They're constants. So this 0 and this food really need to be casted to indicate that they have a certain width before these assignments will type check. Or they should be subtypes. I don't know. So where should these implicit casts show up? But now I can look at this program and say, okay, this type checks. I think this type checks. I don't need any further explanation of how to do it. But I did come up with a lot of questions while doing that. So let's turn to the spec and turn to the implementation and see what they have to say. Unfortunately, it's kind of inconclusive. The spec makes use of notions like type equality and inference, but it never defines them or spells them out, because that's sort of not a priority for the specification. The implementation uses Hindley-Milner to do inference, which is quite a heavy-duty approach. P4 doesn't have proper higher-order functions, and also doesn't have particularly sophisticated generics. There are a lot of restrictions in place that prevent them from getting too fancy. And so it seems like the spec doesn't answer our questions, and the implementation doesn't give a kind of tasteful answer to our questions, in the sense of PL taste, rather. So what we did was write a type checker that goes from a surface AST to a typed AST, inserting implicit casts, doing compile time evaluation, and doing type inference. The type inference algorithm is bidirectional in the style of local type inference, And the implicit cast algorithm is a kind of coercive subtyping check, which is used pervasively in the type checker and can modify the AST to insert the implicit cast. We define type equality and also this subtyping check on canonical types, and we obtain canonical types through compile time evaluation. Returning to our example, and this is just a taste of what goes on in the type checker, of course. There are more issues that came up, some of them less interesting. Returning to the dig, how are we going to evaluate this program now that we've type checked it and spelled out all the type arguments and whatnot? One issue that comes up here is the directions of arguments. So these parameters to f are marked out and in out. An out argument is for function outputs in the sense of a call by reference where the output is being modified. And an in-out argument can be read from, but also used in the same way as an out argument. And here we're reading from the out argument. Is x going to be uninitialized? Or is it going to be the value of x or what? And if so, what will the value of y be after executing the assignment? And then bubbling up, what are we going to get out of f? Is mm going to be modified, or is a copy going to be modified and mm left unchanged? And so what will it be at this program point? This is maybe an easier question to answer in some sense, because we can go and run the program using the compiler and the open source implementation and see what it does. But the fact is that this out parameter is supposed to be uninitialized. And uninitialized things are undefined values. In P4, an undefined value can return anything anytime you read it. We saw it in the first example in this talk. And the implementation sometimes resolves this non-determinism in the front end, taking a degree of freedom, in some sense, away from backends, away from architectures. And we didn't want our semantics to do this for various reasons. So we came up with a semantics that's parameterized over architecture responsibilities. We resolve undefined value non-determinism in the architecture, which is a separate piece of code, which also implements things like external objects and architecture-specific features. You can see the paper for the full details. We use a heap store and closure arrangement to implement scope immutable state, but that's kind of straightforward. We also implement the copy in, copy out calling convention directly. Most P4 implementations, certainly the open source compiler, compile copy in, copy out away. They turn it into a bunch of assignments around each function call. But we wanted to keep it in the semantics so that we could say something about P4 programs without having to reason about a translation. The implementation in general is pretty standard. We begin with a source program, which is P4 program text. We parse it, we type check it, and then we can evaluate it. The parser is interesting. It was written in Menhir, and it uses a Lexer hack. You can see the reference for details on that. It originally developed in the context of C++. We uncovered several ambiguities in the published grammar in the process of building this parser. There's a web-based interpreter where we compile this via JS of OCaml to get it to run in a web browser. And there's also a simple front end, which you can use to run unit tests from P4C. And that's sort of what this diagram is showing. There's a control plane configuration, which specifies the state of all the tables in the program. And there's an input packet. And then the evaluator will produce the output packet and any forwarding metadata involved. Having developed an implementation, we tried to do a selective transcription in the form of a core calculus. It's faithful to P4, but it irons out some of the wrinkles and, in the interest of taste, relaxes some ad hoc restrictions and drops some redundant features. There's a static semantics with expression, statement, and declaration typing judgments, including a compile time evaluation judgment. So we do address compile time evaluation in this calculus. And there's also a dynamic semantics, so you can evaluate expressions, statements, and declarations to get out values and whatnot. And you can see the full details in the paper. We developed some meta theory for this core calculus. The following theorem shows that expressions that type check can be evaluated to a value, and the resulting value will be typable at the same type. This is really a termination theorem, and so there's a simple logical relations argument involved due to the use of closures in the semantics. We also used the core calculus for language design. We added type-safe unions to the language by extending the syntax and extending the typing and evaluation rules. To show that it was a conservative extension, we gave a translation back into the core language and showed that the translation was semantics preserving. This was a proposal, this is important for P4 in particular because there's a proposal in the works for adding union types to the language, but it sort of stalled because it was found to violate type safety. Now, how do we know that Petr really models P4? We think that we should test formal semantics to figure this out. Fortunately for us, P4C, the open source compiler, has a large test suite of examples of programs that should and shouldn't parse, should and shouldn't type check. And then it's also got some evaluation examples where there's a P4 program accompanied by input-output pairs of packets. So you can see what the program is supposed to do to packets. And we wrote some evaluation tests of our own in the course of developing Petr. On the right here, I'm showing the tests that we pass and the tests that we fail. Failing tests are due to, among other things, unsupported architectures or language features, so backends or newer aspects of the language that we don't support, but also disagreements between the spec and the compiler. So maybe not a compiler bug, but something where the compiler resolves more non-determinism than maybe we would like to. And you can see section 5 of the paper for full details on this. Next, I want to show you a demo. P4 runs in a web browser, thanks to JS of OCaml. And the web page and the web interface look like this. There's a P4 program here, which is written in a nice text editor. And there's a box for writing in your input packet in hexadecimal. This is whitespace insensitive. These spaces don't mean anything. What I have here, if you haven't noticed already, is the same example from the start of the talk. And the packet here is the same packet from the start of the talk. It's got a hop that's out port 2, then out port 3, then out port 3. And if I run this, you can see that it produces a new packet, which is less nicely formatted, but is just the same thing that you expect. And it's gone out port 2, so it tells you the forwarding decision as well as the contents of the packet. And if we run that back through the program again, we can see that it goes through port 3, and then finally, as we'd expect, it goes out port 3. So this is great. But let's return to our packet and try to exercise the bug we saw earlier. And that was something like this. The packet's going across a forbidden standard source and destination link, and it's got a hop that has no bottom of stack marker set. So when we run this, we get out something that still has the CCDD, is missing the hop. And what's happened here is that the hops have been all parsed, or the entire packet has ended up being parsed into this hops array. And you can see this by going to the deparser here. This is the deparser, and commenting out the call to emit for the hops. If we do this, the packet we get will be much smaller. As you can see, it's just 2 bytes, one for the type tag and one for the payload, which was the last byte left over. So that's the interface. It's really good for developing P4 programs. We think it's also useful as a teaching tool. Today, to try out P4, you need to install a software switch, a network simulator, and the P4 compiler, which are all pretty hairy artifacts, especially if you're new to the language and not familiar with the intricacies of some of these build systems and whatnot. So I think this is great for P4 just in general as a language and as a community. To sum up, we've learned a few things here. First, POPL-style mathematical tools, this PL toolbox, is up to the task. Modeling individual features usually comes down to finding the right page in a textbook and describing it in that way. But assembling all of that into a coherent overall formalization can quickly suffer from death by 1,000 cuts. and go off the rails and whatnot. And so this is still a difficult task. Next, I think formal semantics evangelism has proved to be pretty difficult. It's easier to convince people to use formal semantics as a foundation for tools, since it increases the assurance in the tool, and it makes sense in that way. But it's a tougher sell to use it as a framework for language design. Language design is already being done a certain way, and we can't expect people to adopt formal techniques overnight, especially if it means slowing down the development of certain things. Now that we have working artifacts, we're interested in doing some more things. First off, we want to mechanize the whole thing in Coq. So port the semantics to Coq, write down some inductive relations, and all that good stuff. And with that in mind, we can move on to devising intermediate representations for compilation or verification of P4. The semantics of the P4 surface language are actually a little complicated, far more complicated than they need to be, considering what P4 targets actually look like. So we think we can find a sweet spot for an intermediate representation, which is lower level than the surface language, but not so low level as to be difficult to reason about. Then we'll develop program logics over these intermediate representations, maybe a HOR logic for proving parsers and programs correct, and also do some compiler verification. We want to build a ComCert style compiler for P4 targeting C or hardware, or maybe just eBPF. So to sum up, P4 is a unifying foundation for data planes, but it lacks semantic foundations. And the Petr4 clean slate implementation gives unambiguous semantics to P4 programs, while the Petr4 core calculus captures the essence of P4. Thank you for listening, and thank you to my collaborators and contributors. And please check out Petr4 on GitHub at cornellmatlab.github.io/Petr4.